Here we go. So as I said, today we are looking at the last two algorithms. And I say two because we're going to look at doing something in two different ways. And so first I'm going to explain what minimum spanning trees are. And then I'm going to show you Prim's minimum spanning tree algorithm and then Kruskal's minimum spanning tree algorithm. And Prim's will go into detail because you'll see it's very close to how Dijkstra works. In fact, it's literally like the same thing as Dijkstra with one exception, which I already mentioned last class, but I'm going to go into detail today. And then Kruskal's algorithm, I'm going to talk about. I'll show you an example, but there's a lot of things I'm not going to mention, but you're more than welcome to look into it. And that's because we have to do sets and unions and just some things that some semesters I've done, but we won't be doing this semester. So we'll focus mostly on Prim, but I do want to bring up Kruskal's and how it works. So yeah, that's the main goal for today. So let's first start out by explaining what a minimum spanning tree is. Now, I know the word tree is in there, but we are talking about graphs, and these algorithms apply to graphs. And we do know that trees are just a form of a graph, right? In fact, a tree is a graph. It's just within a subset of, of the graph world is trees. But the name is misleading because really minimum spanning trees is a type of graph where you try to remove all of the unnecessary edges but still keep the graph connected. So it's like, imagine that I said, okay, I tell you to make a city plan for me, and you come back and you give me all these amazing roads, how all these different points in the map are connected with all these roads you have. And then I'm like, yeah, this is really cool and it's super efficient. People can get everywhere really fast, but it's also really expensive. So we got some budget cuts. So I'm going to have to ask you to basically cut away as many roads as possible, but still keep everybody connected. Now, sure, that's going to increase traffic, but we're trying to make the most smallest, so the minimum, as the name implies, the minimum connections needed to still keep things connected. Now, we can't make new ones. I'm still taking the graph that you gave me. Okay, that person that just claimed the points, you're the same person that claimed them last time and you haven't contacted me who you are. So I don't know who to give the points to. So you gotta contact me. Okay? This is like trolling right now. But yes. So anyways, another example that maybe may resonate more with you is, let's think about wiring. Okay, so same thing. You're a contractor and you're trying to set up internet or some sort of network amongst different houses. And so you're like, okay, the length of the wire is going to be my weight. So, these two houses are close, so you only need like we need to put some units to this. So let's say they are in kilometers, okay? And I don't say miles just because that's kind of long. 2 miles between each house, that's like living out in like the rural areas or something. Even 2 kilometers is long, okay? So yeah, or a server, it could be anything. So let's say there's 2 kilometers there, and then over here we have 5 kilometers here, but here there's only 2 kilometers because maybe like geographically, like you can kind of see how the houses are set up, right? So like, if we were drawing this to scale, it would be like kind of like this, something like that, okay? So then we have another house. This one's 10 kilometers away over here, okay? And maybe here we have a 20 kilometer. It's like goes around some lake or something, okay? And so, you go come back and say, okay, I'm Cox Internet, and this is my proposed, I'm an engineer there, and this is my proposed plan for wiring these 4 houses together, okay? And so I come back and say, yeah, we don't have the money to put all this wire down. So we still want to get all the customers, so we do need to connect them, but let's do it the cheapest way possible. And so you come back and say, okay, what connections here can I remove that, even though it's going to slow things down between them, what can I remove? And so initially, what you want to remove is this 20 kilometer one, because I mean, this is the longest one, right? So you're like, yeah, I'm going to cut this away. And so now you still have everything connected, and you actually lost no efficiency with that one. So that's kind of nice. You lost no efficiency there, but you still have everything relatively connected. Okay. The next thing is, actually, I'm going to change my mind. I'm going to make this 3 kilometers to make a point about this. Okay. The next thing is, you can still cut away more things with this. You can cut away any of these 3. So you can cut away this one, or this one, right? But you want to cut away the biggest one because you're trying to save the most money. So you can cut away the 3 kilometer one. Now, why did I change it to 3 from 5? Because I want to make a point. In the past, if I was trying to communicate between this node and this node, the fastest way was to take the 3 kilometer path, right? But now I got to go a slower way. That's going to take me 4. That's the shortest path. But it's still doable. So with minimum spanning trees, you are sacrificing potentially some of the paths, making them longer than they have to be, but you never disconnect something. So it always has to remain connected. You can just increase it as much as you want. So like, you may have a graph that like you just decide to cut away a bunch of edges to make it the minimum spanning tree, but you cannot just isolate something. So like, you can't, for example, cut away this here, because then you fully disconnect one of the vertices or nodes, and that's not good. But you can cut away all the other connections and just leave one being the cheapest one, hopefully the shortest one, and then you're in business with the minimum spanning tree. So that's why I made it 3 kilometers, because I want to make a point that, if it was 5, it makes sense to cut that because you would never want to take that connection anyways. But with 3 kilometers, it's more of like a harder choice, right? Because you're actually cutting away efficiency. So now it's like you're actually affecting the speed of the network. But Cox is like, I care more about money, so let's cut as much as we can, right? So true story, probably. So yeah, so you go ahead and you cut these 2. And so now this is the minimum spanning tree of the graph. Everything's still connected as it was before. It may not be a direct connection now. You have to go around other places and the shortest paths are longer, but you still have it. So the rules with the minimum spanning tree is going to be, you do not have, there's only one path that you can take for each node. So there's never going to be multiple paths. And you want to keep the smallest edges possible while still respecting the first rule that things are connected. Okay? So that means that if a graph is connected throughout and you have like 10 nodes and everything is at least connected in one way or form, weakly connected as the term was that we talked about, then you will more than likely have 9 edges. So you will have the number of vertices minus 1, such as here you have 4 vertices, so you have 3 edges, okay? So with that in mind, how do we algorithmically do this? Okay, so first let me just show you the paper version of doing something like this. And for that, let's go ahead and take the graph that we used last time, or one of them. We'll do both actually. Let's start out with the top one. So let's get rid of all the squiggly stuff that we did. We did science on this. We don't need those weights. We don't need any of that. All we need are just the edges. So let's clean it all up. Remove that. Also, there's not really a start for the minimum spanning tree algorithm. You just kind of do it. There may be more than one solution to that. For example, if in this graph, the edge that was here was 2 kilometers, in that case, you could remove any of the 3 edges and you'd still have a minimum spanning tree, which means there will be potentially 3 solutions, right? Depending on which edge you remove. So in that case, it's multiple solutions. Okay, so, all right, we got a nice and clean graph, and I'm actually going to maybe back it up, make a copy of it. So you can see the before and after. Okay, so this is the OG graph. And then we're going to have the minimum spanning tree of the graph. Minimum spanning tree, can abbreviate it as MST. No shock there. Okay, so when you're doing this by hand and the graph is manageable, as in like you can actually see it and not get confused, you just go in there and you start yanking out the biggest edges first. And by biggest, I mean they have the highest weight. You start yanking them out or taking them out by erasing them, as long as you don't disconnect the vertex, okay? How do I disconnect the vertex? I remove all edges that are coming into it or coming out. If I do that, then at that point I broke it and there's no longer a minimum spanning tree, it's just a broken graph, okay? So in this case, the biggest edge is going to be the 10, right? So again, think of like you're the cheap and greedy corporation. You want to use the least amount of wiring possible. So you want to remove the, you want to keep things connected because you do want the customers, but you want to remove the longest connections that you have because they use more wire. And so in this case, this is going to be this connection with the 10 kilometers. Like, yeah, we don't need that. Cut that out. We just increase our profits, Our stockholders will be happy. Okay, so bam, remove one. Okay, and now you're going to keep doing this until you can't remove any more edges without breaking the graph. So what's the next highest one that you have? Well, you got the 8 over here. So let's try to get rid of that. All right, I removed that. Everything is still connected. It's all working. The network is good to go. It's maybe less redundant because if one of these wires in a minimum spanning tree, you only have one edge per connect. Like that's basically relying on each vertex. That's very, in the worst case scenario or best case scenario, you always have just one edge, right? Like for example here, there's only one edge that connects these vertices. If any of these edges go down, the graphic is disconnected. So like your network is no longer very reliable, but it's definitely cheap. So happy corporate. All right. Next, let's try to keep removing. So the next smallest one is going to be 6. So let's try to cut that. We cut the wire. Everything is still connected, right? Sure, now we can't just like go through here. And then we got to go through like the long, expensive way. So we have to go to like, oh, what was that weight? We never copied that one. We lost that. Oh, that was a 1. I'm glad, because otherwise I could have broken this. It's a 1. So now, if I want to connect 1 and 4, I have to go through here. So that's like 6, 7, 8, or 9, sorry. So like now, before, let's say this was like a 6 millisecond ping between that. Now it's a 9 millisecond ping, and you're like, oh, I'm getting lag in my game. Yeah, but your Cox is saving money, right? So yeah, so ultimately you keep doing this. Now, the next one that you want to cut off in this case is the 4. Well, you want to try to cut off is the 4, right? Because the 4 is the next biggest one that you have. But this one you can't cut off, because if you cut it off, then you've isolated the 1. And now this is off the network, and then this customer's like, yo, my internet's not working anymore, and they cancel. You don't want it to cancel. You want to take as much profit as possible, but not lose the customer. So that's the minimum spanning tree mentality. You want to remove all the edges you can, but you don't want to isolate or break the graph. Okay? So then you're like, okay, grumble. I'll check and see if there's anything else I can remove. And then you go look at the next 2 biggest. In this case, it's 3, right? So you have 2 options here. So this is going to be a case where you have 2 solutions to the graph. So one of the solutions, and I'm going to make a copy of it because of that. One of the solutions is to try to remove perhaps this 3. And then the graph is still connected. It's just not as efficient. Like I said, you can't go here anymore, so you got to go the longer way. But it's still connected. And in fact, now if you say 1, 2, 3, 4, 5, 6, 7 vertices, and we got 1, 2, 3, 4, 5, 6 edges, we know we're done. But if we didn't want to do that, we could still check. We could go and see what the next 2 are. We try to look at that, but you can't remove that, because otherwise you disconnect the 0 with the 3 and the other ones. You can't remove this either, because that disconnects the 4 and the 6. You can't remove these ones because you disconnect the 6. You can't remove that because you break the thing in half, right? So you only have 2 solutions. This solution and then the one here where instead of removing the top 3, we remove this sort of side tree. So technically speaking, there are 2 solutions for a minimum spanning tree, which are these 2 right here. Okay? So yes, this is how it feels like when your network is the cheapest possible. Yeah, sad. But yeah, so anyways, that's basically how you do the minimum spanning tree. What we've done is actually kind of like the simplified version of Kruskal's minimum spanning tree algorithm. And what I'll show you, again, this is the one that I'm not going to show you to in detail, but I'm going to show you how you actually would do this algorithmically, at least on the basic level. But I'm going to skip an important step into kind of that world. Okay? But yeah, so that's how you compute it. So this is what you can do, for example, on a test. Now, be careful when you do this on a test. My recommendation is just to redraw the graph every single time you're moving the edge. I don't think, unless I ask you in a test, which I don't think I will, to give you like all possible solutions. I think I just do one solution, so you don't have to do what I did here. But you would want to draw it, number them, how you take them out, remove this edge, or just redraw the graph after each edge is removed. Obviously, that only works if you're copying and pasting it digitally. Otherwise, trying to actually physically draw the graph like 10 times will just waste a lot of time unnecessarily. So that's why I say use Paint, because Paint, you know, copy paste, you're done, and this kind of stuff you can do in Paint. But if you have a tablet, that's even better. So yeah, okay. So how would you do this algorithmically? Well, what you got to do is you have to build the adjacency list of this graph. And then once you have that, you just sort the graph by biggest weight, which you can do. And then you're basically good to go. You just start removing from the top and just remove things without breaking the graph. Now that's the part that I'm skipping, how you check that. Because what you have to do for that is you have to use Disjoint Sets. So I'll write that here in case you want to Google it. And I do have a video on this on the 2020 Spring 302 class. If you want to see how you do the Disjoint Sets. It's just something that it gets covered again in algorithms, and I was like, there's no point in covering it now. It's just kind of one of those algorithms that's confusing, and you got to spend some time on actually just what Disjoint Sets are, and you need to have the math foundation to actually understand that. Like unions versus intersects, and just that basic set theory. And a lot of people I've noticed in this class, even though the prerequisite is I think 251 or something, they still struggled with that. So I was like, there's no point. I have to like reteach everything again. So, yeah, but I'll give you the quick and dirty of that. So basically we have the graph. So what I want to do with the graph is build the adjacency list of that. So let's just really quickly do that. Okay, so this goes 0 goes to 2 and 4. Oh, sorry, I was looking at the weights there, my bad. So it goes to 3 and 1. 3 goes with a weight of 2. 1 goes with a weight of 4. Okay, this is all actually in the same line there. Okay, and you're going to do this basically for the rest of them. So I don't think I'm going to do that for all of them because I do want to go to the next step here. But I'll do like the next two. So for 1 goes to 3 vertices. It goes to 0, 2, and 4. So with 0 with a weight of 4, to 1 with a weight of, to 2 with a weight of 10, and then to 4 with a weight of 6, okay? And so you keep doing this over and over again, okay? So when you finish that, you basically have all of the edges that exist in this graph, right? You just, to create them, you just have to basically look up like this is one edge, and then this is one edge, and so on. So what you want to do now is you want to make a list of that. Just make a list because you want to be able to sort it. So for example, of these two that I've made, what I'm going to do now is I'm going to just kind of make a tuple, if you know what that is from like Python world. So for example, I'm going to put the weight first in that tuple. So I know that there's a connection between vertices 0 and 3 with a weight of 2. So I'm going to say the weight I'm going to see from and to vertex, from vertex to vertex. So that means that from vertex 0 to vertex 3, there is an edge with a weight of 2. And that's basically this right here. Now let's go ahead and do this one. So from vertex 0 to vertex 1, there is an edge with a weight of 4. Okay? Let's go ahead and do the next ones. So let's do this one. Actually, let's skip that one for a second. I'll come back to that one. Let's do these two first. So this is going from vertex 1. So we're going to have 3 from vertex 1, right? So we'll see that. We would have 3, but something's going to happen here. 1 goes to, like I said, 2 and 4. And 1 to 2 has a weight of 10. And 1 to 4 has a weight of 6. Now, here's the thing. Here's the thing, okay? So there is that edge going from 1 to 0 with a weight of 4. However, when you're making this list, you want to make it just all the edges. And in this case, this edge is technically the same as this edge, right? So you want to get rid of that and just keep one instance of it, okay? So there's a lot of ways to do that so that you don't have duplicates. You know, coding wise, you just basically, I mean, well, the most inefficient way is just to keep this as a list, and every time you insert an edge, you check the from and to by flipping them and see if that is present. So like if you're trying to insert 1, 0, check if 4, 0, 1 exists. And then if that exists, then don't insert it, right? So that would take n time every time you insert one edge. Alternatively, you can use a set and just, you know, build it as a pair and see if that is present already in that set. And that's a little faster because you're using power of hashing and so on. Okay. So what we're going to do with that is we're going to build a list of edges. And this list should be the same amount of edges that you have in the graph originally. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, we're halfway there almost. I'll do the rest of them. So let me just copy the graph down there so I can see it. Okay, and then just so I don't get confused, so we did the first two. This is the next one, so that's vertex 2. Vertex 2 has 3 edges going out. Some of those are duplicated though, but let's just throw them all in first and then figure out the duplicates. So it goes to 2 to 3, 2 to 5, and 2 to 1. 2 to 3 goes with a weight of 3, 2 to 5 goes with a weight of 3, and 2 to 1 goes with a weight of 10. Of these, we already have present the 2 to 1, right? So we can go ahead and just erase that from here. Okay, moving on, we have vertex 3. Vertex 3 has one edge going from 3 to 5 with a weight of 1. And then it has edges going from 0 and 2, which we already did, so we don't have to worry about those. Vertex 4 has an edge going from 4 to 6 with a weight of 1, and from 4 to 5 with a weight of 2. There is also an edge going from 4 to 1 with a weight of 6, but we already have that in our list, so we would not include it again. Okay, and so I think we have all the edges now. We have 2, 4, 6, 8, 9. Oh, we're still missing some, I think. So 5 goes to 6 with a weight of 8. And then I think that's the last edge that we have. So then we have 10, 2, 4, 6, 8, 10. But I thought it was 11. 2, 4, 6, 8. No, there is 10. Okay. So once you have that list completed, you're going to sort it. And you're going to sort it in increasing order for the, actually, well, technically, sort it in decreasing order for the weight. I'm trying to make it smaller, but it won't let me. Okay? I know what I can do, though, so that things are not so tiny. I'm going to shrink this out, but then I'm going to zoom in. Yeah, all right, technology, science, magnet. How do they work? You all seen that meme? Okay. Close enough. All right. So now, actually, let me, what's the easiest way to do this? I think I can just, if I get rid of these columns, then it'll work out much easier. And then I just duplicate it. Okay. So let's go ahead and sort this. So that goes at the top. And what do we got? We got the 6 to put in there. The 8. We have a 4. And then we have the 2. Oh, that wasn't efficient. My bad. You're just sorting on the key as a key of the weight. You don't look at the edges for that, okay? Which meme? The clown posse video with the magnets, how do they work? But yeah, okay. So now, we have a sorted list, okay? That's very sad. It's one of the original funny stuff. It's like if you just want to laugh for a while, just watch that video. But it is definitely old. There was even an SNL skit on that at some point. That's pretty good too. It's like a parody of a parody, kind of. It's like deep. It's like inception of parodies, recursive parodies. But yeah. Okay, so now that it's sorted, you just basically work your way down from the top. And you have to just make a decision whether you should remove that edge or not. And so this is where the disjoint sets come in. So as you do this, you start building sets. And then when you're building the sets, you actually, oh, no. I apologize. No. When you're building it with disjoint sets, you work your way from the bottom up. So actually, we're going to work our way from the bottom up. So, because what you do is kind of like the backwards version of this a little bit, where you're building the edges by going with the cheapest ones. And then the disjoint sets is used because if you have a cycle, that's when you stop, because you're like, okay, there's a cycle. So again, this is for your own personal benefit. On the test, you just have to do the drawn version or Prim, which I'll show you. Although I think I might offer extra credit for showing both versions on the test. I don't know. I did that in the past. Maybe I'll do that again. But yeah. So this is for your benefit. Okay. So what you do is you start out by just basically making sets of all the edges. So you go from the bottom. So we say, what we want to come up with is a list of edges that make the minimum spanning tree. Okay? So actually, I'm going to copy and paste it again so that I can just pull things out as I want them. So I can get rid of these lines because otherwise I know those are going to be a pain. Okay. So let's start with the first edge. So pick the smallest edge. And we currently don't have any disjoint sets. Or any sets, I mean, so we are just going to throw those two edges into those vertices into the set. So these sets don't really have names to them. I can either draw them like that, or I can draw circles and just throw them in, either or, whatever works in your head. But I think it's better to do it this way because this is more like code-like that you're building this set per se. Okay, so you have that set. Cool. That also means that that edge is part of what it will be the minimum spanning tree. All right, next one. We have 4, 6. We don't have 4, 6 anywhere, so they now become their own set. They're separate sets, okay? So we have 2 sets here. Next, we have 4, 5. So 4, 5. So 4 and 5 are already present in our sets, but they're in separate sets. So what we want to do is we want to find the intercept between those two sets. And if that intercept has something in common, then we have found a cycle. And that means that this is no longer part of this edge would not be part of the minimum spanning tree. The cycle detection algorithm and doing those intercepts, that's all math, right? So you're making the intercept between two things is what they share in common, right? So if you have a set that's A, B, and this is where I don't want to go too deep here because this is your math. These sets are not, they share nothing in common, right? But if I have something like this, then technically speaking, they share the B in common, right? That's what we don't want. We don't want them to share anything in common because what that is saying is, if you think about it from like a graph perspective, we're saying that there exists an edge that's like that, and there exists an edge that's like that. So what that means is that B and C are already connected. So there's no reason to add in an ASC to edge because that would make a cycle. Okay? Oh, little hand waving there. But yeah. Okay. So now we basically say, oh, okay. In this case, we have a 4 here and we have a 5 here. So we're gonna take we do the intercept. The intercept is clean. So then we union them together. So now we have a set that has 4, 6, 5, and 3. Okay, next, let's go ahead and take the next edge. 2, 3, and 0. Okay, we have 0 and we have technically 3, but the 3 is already present in one of our sets. So therefore, we are going to put the 0 in there as long as it's already not present. If it was present, so technically, you can think of it as doing an intersect between this and this. And because that is clean, there's nothing in common, then we're good to go. So we basically throw in the 0 in this set. All right, moving on, 3, 2. Same situation here. We have a set with 2 and we have a 5, but 5 is part of the other bigger set. So we do the intercept is clean. So then we say, okay, we are green, green light to add the set. It's becoming a bigger set here, big set. Oh, that's not what I meant to do. Let me just bring it down here. Okay. Next, let's take out 3, 2, 3. In this case, both the 2 and the 3 are already present here, right? So if we try to do 2 and do an intercept with this, then we would see that there is something in common, which is the 2, right? So they're not disjoint. So basically, that means that this is an unnecessary or redundant edge. And if we added it, we would create a cycle. And so therefore, we don't want to add it. We discard it. Okay? So delete it. Yep. So moving on. 4, 0, 1. The 0 is present there, but we don't have a 1. So therefore, we would throw it in. And at least in Python, it's tradition to use parentheses for sets. So that's why I'm using parentheses. Next, 614. This one, as you can see, the 1 is here and the 4 is here. So that's a redundant edge, would create a cycle, so we don't want it. Okay. Next, we have 852. 856. Both the 5 and the 6 are already present in our set, so that is a no-go. We basically get rid of it. And finally, we get this one. Yet again, 1 and 2 are already present, so we don't want it. So then we have, I feel like did we lose an edge that we weren't supposed to lose? No, that's good. There's how many there? 2, 4, and 6. Oh yeah, believe in the algorithm. Believe in the science here. This is actually correct, as it is. Oh, snap. There we go. Okay, so this is your minimum spanning tree. So if you want to draw this graph, just convert it back to a adjacency. So, you know, 0, 1, 2, 3, 4, 5, 6. And then it's going from 0 goes to 3 and 1, goes to 3 with a weight of 2, and then goes to 1 with a weight of 4. And then for 1, it goes to nowhere. It's just that's the only edge for 1. It's the one that we already put. So just 1, it goes to 4 with the weight of 1, and so on. So you could build that, but you could also just use that directly to build it. But you get the idea. So at that point, you're done. Again, this is your weight, this is your from, and your 2 vertex. So this is the only edges that you need to have for a minimum spanning tree. Okay, so that is basically Kruskal's simplified. But again, that disjoint set stuff is its own thing. Like you could code it as your own assignment actually, and it would be its own thing. Like in some languages like Python, like I said, there's actual sets. Like that's a data type. So like just like there's list, and so like it just makes it life super easy. You just go and code a set, and then you just use the operations on the set, the union, intercept, and whatnot. And it's super fast. I love them. It's great. But hey, we don't use Python in this class, so you're all stuck with C++. I'm sure there's libraries though that you could probably use if not for this class, but like in life in general, if you really had to. Okay, so for let's use the same graph that I used in the past for Dijkstra, because I do want to show you the comparison. So let's take this graph. It's a very colorful graph. I like it. So let's take this graph and let's go ahead and perform prims on this. So prim is going to be very much like Dijkstra. Like if you're not careful, you accidentally do Dijkstra instead and you get the wrong answer, or vice versa, which has happened to me before. I think in spring of 2020, I totally screwed up, and like I was teaching Dijkstra and I was teaching prims, and I did that so nowadays I do Dijkstra and then I do the minimum spanning trees, but I think that semester I was doing minimum spanning trees and then Dijkstra. And when I was doing minimum spanning trees, I literally did the Dijkstra algorithm. And at the end of the class, I was like, oh shoot, I think I did this backwards, guys. Never mind, this is actually minimum spanning tree, not Dijkstra. So I felt very bad about that. So I re-recorded an entire new video just because I didn't want to confuse people. But yeah, so sad days. Okay, so if you recall, in fact, I'm gonna actually take that table that we have for Dijkstra, and I'm gonna take the table and the algorithm, because I want to show you the only change that I'm gonna make to the algorithm that will make that difference. Oh, you did this something. That's like taunting, because it's like the end of the semester now. So they don't get to reap anything. Okay, so we have the same graph from last time, and we have the same table. I'm just going to clean up the table. Okay, I think it's clean now. Oh, no, I gotta remove the parents too. Remove the parents. Sounds very evil. Leave the child alone. Okay, cool. So now I have my code, or I have my algorithm, better yet. And so what do I need to change for making this into Prim's minimum spanning tree? I believe Prim's is spelled Prims. I think it's 2 M's, but let me make sure it's not an M and an N. Oh no, neither. It's just 1M. Okay. So Prim's minimum spanning tree. Okay. This is the good one. This is the one that you probably should just learn, because, like I said, it's very close to Dijkstra, so might as well not like use extra brain capacity. So, okay. In here, all you gotta do is remove. I believe all you gotta do is remove this addition. You don't want to add the weight. Or actually, no. Remove the U key part. Yeah, remove this. Just leave the weight part. So before it was an addition, now we're just making it the weight. Similarly here, remove this. That's probably why I had to highlight it. Now that I think about it, I mean, I don't know, it's been a while, but that's probably why I had to highlight it, because that's what you got to remove. So yeah, that's it. Done. It's literally, if you were coding this, all you got to do is remove those 2 pieces of code and you're good to go. You have now converted this Dijkstra into minimum spanning trees. So like when you're like, hey, I want this, you're like, we have Dijkstra at home, and then Dijkstra at home is like minimum spanning tree, other meme. So yes. Okay, now this might not make sense to you right now. You're like, huh? What did you just remove? Like, I'm confused, because I mean, you just learned Dijkstra like 2 days ago, so that's okay. So I'm going to show you what I actually did. So in the past, if you started this algorithm, we know that we start in Dijkstra, we start at the starting node, which we have to choose. So with minimum spanning trees, it doesn't, again, like I said, minimum spanning trees don't really have a start or an end. You just pick a node. So just pick one to do prims. In this case, not coincidentally, we're going to pick the same starting node as we did before, just so you can see the at the end how close these things look. So just have to make a decision. It doesn't matter in Prim's case which you decide to be the starting node. Okay, so again, we're just going to say, we're going to pick 0 for the heck of it. So 0 goes to 1 and 7, right? So in the first step of this, it will look identical to Dijkstra, actually. So that's why it's very easy to get confused. So you're like, okay, because it goes from 0 to 1, that's vertex 0 to vertex 1 with a weight of 4. We go ahead and we say, okay, we put a 4 there for the weight. We put the parent at 0, and we're good to go. And then we do the same thing for 7, which is a weight of 8 for the edge, and the parent is 0, right? So right now it is the same as Dijkstra. No difference. Next step, just like Dijkstra, you pick the smallest one to continue. So the smallest one of the 2 options that we have is basically vertex 1, right? So you go to vertex 1. We're going to mark that as visited so we don't forget, because I tend to do that. And then you see that vertex 1 has a connection to 3 vertices: vertex 0, vertex 7, and vertex 2. Just like with Dijkstra's, we don't want to touch vertex 0 because that's already marked as visited. Now, in the case of Dijkstra, let's go ahead and do the Dijkstra version of what you would do here. With Dijkstra, for the vertex 2, you would take the current value of vertex 1, so that 4, and you would add the 4 plus the 8, right? Because you're adding both this and this to get to the 2, which is equal to 12. And then you would compare 12 with what is currently there, which is infinity. So you would go ahead and put 12 there, and you would set the parent of that as 1, right? That's that Dijkstra world. In Dijkstra world also, for the 7, you would do the same thing. For the 7, you would be like, okay, I'm going to take the current value of the key for 1, which is 4, and then I'm going to go ahead and add 11 to that, because that's what we have here, 4 plus 11. So that's 15, right? 4 plus 11 is 15. And so you would say if 15 is smaller than what is currently on 7, which is 8. That's not the case, so you would not update it, and you would call it a day, right? That's all you would do. That's Dijkstra land, but we're not in Dijkstra land. We are in Prim's land. In Prim's land, you don't do this. In Prim's land, instead of saying 4 plus 8, what you're going to do is you're just going to look at the edge that's coming in from the previous vertex. So you're currently at 1 and you're going to 2. So you're just going to be looking at this edge and the weight associated to that. And you're not going to add this old value to it. So really, you're just comparing 8 with what's currently there, which is infinity. So this is, of course, better than infinity. So you could put 8, and you still put the parent as 1. So that's the only difference. So before, you add what you how long it took you to get there, plus whatever it is to go to the next one, right? In prims, you don't do the addition of that. You just take the edge and that's it. Similarly, for the 7, from 1 to 7, we have 11. Before we would add 4 plus 11. Here we're just going to look at the 11 and actually compare that with 7. But it happens to be that 11 is still not less than 8, so you still don't update that one. So there you go. In Dijkstra's world, you would put there a 12. In Prim's world, you put an 8. That's literally the only difference. That's it. As long as you do that difference and you do the rest of this, it'll be identical. So because we still have half an hour of class left, I'm going to go ahead and do the entire example. But that's all you gotta know. Bam, you're done. This is literally Prim completed. Okay? So let's go ahead and do that. So we have two to choose from. They both happen to be 8. This tells us that it could be a situation where, like, you know, one of these is there's more than one answer to this graph for this minimum spanning tree, basically, when we have this decision. So we're just going to pick one. We're going to pick that one just because it's literally next to that. And so we're going to mark it as visited so we don't forget. And let's look at all the edges coming out of the vertex number 2. So we got 4 of them. We got this one, this one, this one, and this one. So let's go ahead and handle them. So we don't have to worry about this one because it's going to a visited vertex. So we only have 3 of them to worry about. So let's go ahead and do them. So 2 to 3. 2 to 3 again. In the past, we would have taken the weight of 2, which is the key of 2, which is 8, and we would have added that to the weight going from 2 to 3, which is 7, right? But again, in Prim's world, we don't do that. We just look at that and put it in. So we just look at the 7 and put it in there and put the parent as the 2. So that takes care of the top one. From going from 2 to 8, same thing. We only put the 2, which is the weight of that edge. We don't add anything to it. It's kind of trippy, but you don't. And then again, make sure you don't forget to put the parent. And finally, from 2 to 5, there is currently a 4. And the parent is 2, of course. It's very easy, but also very easy to get confused between both algorithms, okay? So, yeah, just be extra careful about that. Okay, pick the next smallest one. That's going to be this one because it's a 2. The other one has a 4 and an 8 and a 7, so those numbers are bigger than 2. So, yeah. Where is 8 on the graph? 8 on the graph is here. So we got 3 potential ones. One of them we don't need because it's going to a visited node. So we only got to look at 7 and 6. So for 6, there is a 6 as well. Again, we're not adding. We're just looking at this 6. Parent is 8. And then for 7, there is a 7 here, right? 7 is smaller than 8 that we currently have. So that means that we are going to replace this 8 with a 7 and make the new parent, which is 8, right? So again, we're replacing it with the edge. That's that edge. We're not adding stuff from before like Dijkstra. We're just replacing it with that edge, and that's why we're comparing that. So go ahead and achieve that. And you see, I forgot. I gotta mark that as visited before you move on. Okay, so that takes care of the 3 edges because again, one of them was already going to a visited vertex, so we don't have to worry about that. So now we gotta pick between 8, 7, 4, 6, and 7. 4 is the smallest of those, so we're gonna go with that. Mark it as visited. So what's coming out of 5? So 5 has that edge, that edge, that edge, and that edge, right? So of those, the edge going to 2 is taken care of, so we don't need to worry about it. And everything else we got to do. So let's start. So the one going from 5 to 4 is 10, which is better than infinity. So let's just throw that one in. The one going from 5 to 6 has a 2 in it. We currently have a 6 there. 2 is smaller than 6, so we are going to change that to a 2 now and update the parent to be whatever we're looking at, which is a 5. All right. What about going from 5 to 2? Well, going from 5 to 2, we don't update because we already have that That's weird. That's fine. We already have that edge, right? We already have the edge from 5 to 2. So we don't want to update that at all because it's already marked as visited. See, this is a part where you're kind of misled to think that you would want to update that. You're like, oh, well, let me update the 5 to 2 because it currently has an 8 with a 4. But no, don't do that. Bad things will happen. This will probably break if you do that. So yeah, it's trippy. Like, I feel like something's wrong there, but we'll keep going. Okay. So moving on, we got 5 to 2, 5 to 6, 5 to 6 is a 2. We did that one. 5 to 3 with a 14. That's definitely not efficient. So nothing happens there. Yeah. Okay. That takes care of all of them. So now we have 3, 4, 6, and 7. 6 is a 2, so we're gonna do that one. 6 goes to 5, but that's visited. 6 goes to 8, but that's visited. 6 goes to 7 with a 1. That's good. We want to update that. It's better. 1 is smaller than 7. Okay. And now we go there. So with 7 going to 0, we don't worry about. 7 going to 1, we don't worry about. 7 going to 8, we don't worry about. And 7 going to 6, we don't worry about. So there's nothing that gets updated. Mark that as done. We go to the 3. So the 3 goes to 2, and it goes to 5, and it goes to 4. So the only one we can update is the one going to 4. And we do update it because it has a 9. And so now we want to put, or so it has a 9, and we currently have a 10. So that's 9 is smaller than 10. So go ahead and update that. And then you're done. And then when you're looking at the 4, like the same thing happens with Dijkstra, where when you only have one vertex to look at, you don't even need to look at it. We can turn in both attendance extra credit points, right? Yes, you can. Yes, you can do as many as you can maximize, basically. So, yep. And then the last day is next class as well. So yeah, this is it. Hopefully it's right, because that does feel weird with the 8 still being present. But you know, Dijkstra says this is the way, so this must be the way. All right, so let's see. If you want to see, I mean, this is the answer. You have all the edges here, but if you want to draw the graph, you can do that. The way you do that is, here, let me actually copy everything over. So if you want to draw the graph, what you're going to do is just get rid of all of the lines for now. Just leave the vertices where they are. Very artistic looking graph here. I like it. Okay, so now go ahead and draw these pairs like this. So those pairs, all of these pairs you want to draw. So for example, 2 to 8. Where's 2 and where's 8? 2 to 8. And what is the weight of that? 2, because that's where that is. So this is all the weights. And then it doesn't really matter, but you can think of this as like a from and a to. So that one's that one. So, okay, next one, 6 to 7. So 6 to 7 with a weight of 1. All right, 5 to 6 with a weight of 2. All I'm doing is I'm looking at these pairs and just working it this way. So I'm going to do next, I'm going to do 5 and 2 with a weight of 4. So 5 and 2 with a weight of 4. 3 and 4 with a weight of 9. 3 and 2 with a weight of 7. 1 and 2 with a weight of 8. 1 and 0 with a weight of 4. And that's it, because there's nothing here. This doesn't count. So, is this the minimum spanning tree? Could we have come up with something better? Let's quickly do it by hand, just to verify. This is the one we said, just remove from biggest to smallest. So definitely remove the 14 first. The next biggest to remove is going to be the 10. We can't remove the 9 because that would disconnect the 4. So we move on to removing the 8s. And so we have two options. It's the same thing that happened when we were doing the Dijkstra. So let's just stick with the same option we chose for this one, which was to remove... Oh, did I draw that wrong? 1 to 8. Yeah, I drew that wrong. This was supposed to be 1 to 2 with a 8. This is not supposed to be there. That's from here. Right? Yeah, so I drew that. That was my bad drawing it wrong. But yeah, so if we do that here, we got to choose one, right? So let's just say we choose this one just so that it matches what we did on the decision when we're doing Prim. So after that, oh, sorry. Before you remove either of those, remove the 11 because that's bigger, right? Remove the 11 first. And then you try to remove the 9, but you can't. So then you remove one of the 8s. After that, you got to remove one of the 7s. So you can't remove this one because that would break the 3 and the 4, but you can definitely remove this one. So let's remove that one. For the 6, you can remove the 6. Yeah, it won't disconnect it. Is there any 5s? Nope. 4s you can't remove because it will disconnect it. Like that would disconnect that, and this would disconnect that. There's no 3s. You can't remove 2s. You can't remove 1s. You're done. So now, does that look the same as what we had? Yep, that looks identical. So as you can see, it's a little bit not so intuitive that it works, because like this 8 was weird that it stayed there, but it works. So that is Prim's minimum spanning tree. Yeah, it's like it's a form of magic indeed. Yep. So yeah, it'll work. Like I said, you know, 2 birds with 1 stone. If you remember Dijkstra, you know Prim. You just got to remember to change that little addition. So I don't know where you're all at with your assignments, but technically speaking, from a coding perspective, once you code one, you basically got both coded because you just got to literally remove that plus sign and that update. Just those 2 spots, remember, that I removed. Let me go back to the Dijkstra's code. So I removed literally the stuff that's highlighted on pink. You know, remove the U key plus part and remove the U key plus part there. Just leave the WUV. So yeah, as long as you remove that tiny piece from your code, you have essentially have both of them already coded. If you've done one of them. So yeah, both are great. Both are efficient. I think in the test, I asked you to do one of them. It's your choice what you want to do. If you want to do the draw version or you want to do this table version. The same warning goes that went with Dijkstra. Be careful with the table because it's so easy to make a mistake. Like it's easier for me because again I'm talking and doing it and moving and everything. But if you just do it on you're quiet and you have no distractions when you do the test, then it's a little bit easier to not screw up the numbers. And you can always verify, like I did. You know, verify that you actually got a right answer. Just like it took a little bit to do verification. You know, maybe 1 or 2 minutes. Actually less than that. Maybe like 1 minute. But now I'm like confident that the answer is right, yeah? And at least you can do this for the test. So you can like be sure that this is good, right? So check your answers if you have time. You do have 2 hours for the test though, so that's nice. Okay. Any questions? We have 15 minutes still left. So first let's see if there's any questions about minimum spanning trees. And if there aren't any questions on that, then I guess just any questions overall for the final, basically. Next Monday, I have no new material. I will just open the floor for any questions on the final or any questions on the class material. If no one has any questions, maybe I'll talk a little bit about P and NP and that kind of stuff. So you know it. But again, I also have the bonus video for Wednesday. So if you don't have questions today, do make sure you bring questions next class if you want a review. I mean, if you know everything, you're good to go. What other language do we work with out of degree? It depends on the classes that you take. You will more than likely work with Java in the compiler course and possibly on the 326 programming language course. That class, you work on a couple of languages depending on if you take it with like John Miner or Matt Peterson or Ben Cisneros. Depending on who you take it with, they do different stuff. But compilers, you have to take with Peterson. He does Java, so Java for sure. If you take some of the machine learning courses, you do Python. I think it's a neural network class with Dr. Gefontis. You do C#. But most of these classes, there's no like 135, 202. You just kind of go there and they're like, yeah, okay, here's an assignment in C#. If you don't know it, go learn it. So, you know, you are expected to pick it up quickly. But I do think that Dr. Peterson does has like his TA do like Friday crash course on Java so that you can at least learn it if you don't know it. Can you go over certificates for NP? Are you talking about certificates like what I said before in terms of like recurrence relations? Where like I said like for n belongs to O of n as long as what was it like NC where C is greater than 4 or something like that. Is this what you're talking about? What we did like early on? Because if you're talking about like proving that something is if you're talking about proving an algorithm that belongs to a certain class, like if saying like the knapsack problem belongs to the NP class, then you have to do a reduction. It's known as a reduction, and that's hardcore. You'll do that in 477, but I'm not going to do that in this class. I mean, I do have in that bonus video. I think I do a reduction to the SAT problem, but of a different problem. But yeah. No, well, I think what they're talking about is that. It's called a reduction. So if you have a problem, for example, well, you have to know what this Boolean satisfiability problem is. So the Boolean satisfiability problem is like I have a if statement where it's like if A, you know, or B and C or D, and then just put like 50 of those in the line, right? And I tell you, give me all the possible answers that that this will actually return true for. So you could be like, well, you know, because I have an or statement here, let's put this in parentheses to make it harder. Then I can say, well, if A is equal to true, then it doesn't matter what B, C, and D are, so they could be false or true. And this will, either of those will be valid answers, right? Alternatively, if B and C are equal to true, A can be false and D can be false, right? You could also have A be false, B be false, C be false, and D be true. And then I think it also evaluates to true, right? So basically trying to come up with a list of all possible solutions that would give you this if statement to true is a hard problem to do. You cannot do an algorithm that can do it in polynomial time, meaning you can't do an algorithm that takes like O(n) squared. This is math, this exponential basically, and so or non-deterministic polynomial, meaning that is not easy. And so we know, or we've sort of accepted that this problem belongs to the NP class. And so if I come up with a problem that is kind of like this problem but wrapped up and looks totally different, so like the knapsack problem is like I have a backpack that can carry like 10 pounds of content, and I have a bunch of boxes that are different pounds. And I ask, you know, what's the best combination of things that I can put in here to maximize the capacity, that kind of thing. This is also an NP problem. Converting this problem into the satisfiability problem is a matter of doing math on it. And if that math takes polynomial time to achieve, then that means that the non-polynomial part of this problem is what is making it hard. So therefore, you are reducing it to a problem that we know for sure. So it's like saying, okay, I know that I know that lifting a table upstairs is hard. So if I say, okay, lift a couch there, if you can say that the couch, if I can convert a couch to a table within polynomial time, that means that the couch is just as hard to lift as the table is, as long as that conversion takes polynomial time. If that conversion takes NP time, then you could say that the problem itself is not NP. So if all of this doesn't make sense, that's okay. I mentioned this in the video, and they'll talk about it in 477. But yeah, it's called a reduction, basically. And so, yeah, like 99% sure it's called a reduction. Because certificates is like the stuff with recurrence and stuff. So, no, I've never really heard the word certificate mentioned into the context of P versus NP. Well, there's a bunch of them too. Like, you learn a lot of them in 477. Like, you'll spend a considerable amount of time on this stuff. So yeah. You at the very least you'll be doing SAT problem, knapsack problem. Those are the ones that like come to my mind, but there's a bunch of them you cover in that class. So yeah. I worked with Java in high school. That's nice. But I think Python's better. It's just so nice. You just code and it works. Like, you don't know why it works, but it works. You're like, okay, cool, it works. Anything else? We still got 7 minutes of questions. I mean, nothing for minimum spanning trees, first of all, because that's what we covered. Like, are you all good on that? You all good with the assignments? You know, easy minimum spanning tree coding. It's unfortunate that like the last 2 assignments are kind of cramped at the end, but that's why I make the final open early on so that you can at least get most of it done minus the Dijkstra part if you're waiting for that. And that's why I flipped teaching Dijkstra first, because it's a lot harder to grade CSBO than it is to grade the other assignments. So I thought get that one in first. Okay. Well, if there are no more questions, like I said, next class, bring questions. You know, I know it's Thanksgiving weekend and Black Friday, but at least while you're waiting on Black Friday, you know, start thinking about the final and what you want to review. If like you want me to revisit hashing or anything specific, I will. I'll also tell you the distribution of the test on Monday. But like I said, the majority of the test is focused on these, so you can expect like a minimum spanning tree question, a Dijkstra question, traversal question like breadth first search or depth first search, or maybe both. You might get something on topological sort. You might get like a terminology thing with the graphs. So that'll be like the meat of the final will be on that. But there will be a smaller section that will be some of the OG questions. So like maybe like an ABL question, maybe a recurrence relation, maybe, and maybe like a tree building one. Because those were like the big stuff. Oh, and the sort one probably too. But like I said, you know, the majority will be focused on the new content because that's what we haven't tested you on. The other stuff is just like the key stuff that we learn. Like, I mean, we learn a lot of things, but like, who cares about like selection sort? You know, when like heap sort and quick sort are like, or merge sort are like the big ones, right? So you can, you know, I highly doubt you would get a selection sort question, but you might get a heap question. Okay. Well, I see no comments on anything, so I will presume that you're all good to go. And like I said, just come prepared with some questions. And you know, worst case scenario, if the class doesn't go full time next time, then that's okay. So, will we get another worksheet? You know, that's a good question. I don't remember. Let me check. I don't recall there being a worksheet, but there might be. Let me see. Nope. I don't think I have one. I don't see a worksheet for that. I do have links on Canvas for minimum spanning trees, algorithm analysis. I think there's a, let's see. Oh, ABET. Shoot. A reminder. Do the ABET test. That's a good review for the final. It's like a test you take, and it's graded. But it's graded as in like, well, yeah, I shouldn't have to grade. It's graded as in like you get a completion grade, but you know if you bomb it, for example, you don't lose points or you don't gain points if you ace it. But you should take it seriously because you can use this as a study guide. So like, I mean, actually, I know that I have it due on the 30th, but I would encourage you to take it before next class because what you get wrong there, then I can actually, then you know what you need to refresh. Like if you really screw up, like there's a question on traversals, right? Well, I hope you know traversals. That was kind of easy on the easy side, but like if you really just bomb a traversal question, then you know that's something you want me to review. So take the ABET test, okay? That's an evaluation for UNLV accreditation thing. So you want to do good on that because you want UNLV degree to be like good in the world, not like bad. So yeah, take the ABET test. That, I guess that's kind of in lieu of a worksheet what you can do. But yeah, I don't see any worksheets or anything like that. I might want to make one next semester. The problem is that at the end, it's just everything is last second. It's one more thing to worry about. But maybe at least I'll do one like for no points, so you could see that. But I mean, you can. I try to describe to you what the final questions will be like. So yeah, I don't know if I have time to make one now, but next semester maybe I'll do something. Well, I don't even know when I'm teaching 302 again. Might be another year. I thought I had a final exam like study guide thingy, but I don't see it either. Graph references. Nope. That's fine. Like I said, if you want me next time, I can come up on the spot with some pseudo practice questions and we can work through them. So you can see what the questions would be like. I already have the final pretty much done. I might tweak it a little bit, so I can give you mock questions. Like for Dijkstra, I give you the graph and I give you the table. Like I give you like a table like this, blank. And I say, you know, here it is. Go for it. You know, so you just makes it easy because you can just print screen, open Paint up, copy paste it a lot of times, and fill it in if that's what you want to do. So for minimum spanning tree, yeah, I give you a minimum spanning tree and I ask you use Kruskal or Prim. Here's the tree. Go do it. Extra credit if you do both. So. And these graphs are drawn here, so I will try to make them as clean as possible. So, but hopefully they are clean. But yeah, there's no tricks to this. Okay. All right then. Well, since there's no more questions, like I said, I'm warning you. You better come in with questions, otherwise we'll have nothing to talk about for next class. And next class is the last class, right? Because I mean, we're done. No class on Wednesday. So there's the bonus video if you want, but there's nothing official. So all right. Well, having said that, we are out of time now, so I will end it. Let's stop the recording. Okay. So yeah. Have a great holiday weekend. Hope you all stay safe and get to see everybody you want to see and everything, and do your shopping. Don't 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 go into war with the shopping. Crazy stuff running around. But yeah, take care, everybody. Stay safe, and message me if you need anything. See ya.